Alrighty, folks, hello and welcome back. In today's lesson, this is lesson number 3, or the beginning of lesson number 3 at least. We're going to be talking about the RSA algorithm in cryptography. So this is our first application of all the tools that we've developed up to this point in time, which isn't a lot, but we get something really cool out of it already. So the RSA algorithm is the most widely used asymmetric encryption algorithm deployed to date. Now, what does that mean, asymmetric? Well, asymmetric actually means that it works on two different keys. There's a public key and a private key. And as the names describe, the public key is given to everyone, where the private key is kept, well, private. So as an example of this asymmetric cryptography, suppose we have a client or a web browser. It sends its public key to a server to request some data. Now, the server is going to encrypt the data using the client's or the browser's public key. Then it sends the encrypted data back. Now, the client or the browser receives the data, and since it also has the private key, is able to decrypt this. So since this is asymmetric, nobody else but the browser can in fact decrypt the data, even if, say, a third party had access to the public key. So you have to have both keys to be able to encrypt and then decrypt the code from there. All right, so the acronym is derived from the last names of the three mathematicians who created the algorithm. This was back in 1977, so we have Rivest, Shamir, and Edelman. And in order to understand the algorithm, we need the following three properties. So we're going to develop the math needed behind all of this, and then we're going to run through how we actually use the algorithm on a simple example. So in order to do this, we need the first lemma. So let P, R, S, and C be elements of the integers, and P is prime. Now, if P does not divide C, and RC is congruent to SC mod P, then what has to be true is R is congruent to S mod P. So let's go ahead and let's prove this one here. So this is our lemma, or proof of lemma. Okay, so what are we given? We're given that P does not divide C, and that RC, the product RC, is congruent to the product SC mod P. All right, well, by definition, if I look at that congruence, well, what does that mean? If RC is congruent to SC mod P, that means P divides the difference between those two. So P divides RC minus SC, or we could rewrite this as P divides. I can factor out the C, so I'm left with R minus S and C. Well, let's make this S a little bit nicer here. So R minus S times C. So I have a prime that divides the product of two things. Now, from a couple lessons ago, what we showed was if we have a prime that divides a product of two things, then it has to divide one or it has to divide the other. So since P is prime, again, either P is going to divide R minus S, or P is going to divide C. But here's our problem. We already know from the assumptions of the lemma that P does not divide C. Since P does not divide C by assumption, then P has to divide the difference between R minus S, which again implies that R is congruent to S mod P. And that's our proof. All right, so what else do we need? we're also going to need Fermat's little theorem. Now, Fermat's little theorem states that if P is a prime and A is an element of Z, and of course P does not divide A, then if we take A and we raise it to the power of P minus 1, this is congruent to 1 mod P. So this is any A that, again, when I raise it to the power of P minus 1, is congruent to 1 mod P. Now, we're not going to prove this one, but let's show an example of this. Let's get some more space here. So just an example. Let's look at 5, which is an element of Z, and 7 is our prime. So if I'm doing this in Z mod 7, the elements that I have inside of there are, if I'm grabbing the representatives, are from 0 all the way up to 7 minus 1, which in this case is 6. So if I raise 5 to each one of those powers, we're going to see I hit 1, or it's going to be congruent to 1, when I raise it to P minus 1, which again in this case is 6. So if I take 5 to the 1, well, that's equal to 5, which is still congruent to 5 mod 7. 5 squared, well, that's going to get us 25. If we divide out by 7, our remainder is 4 mod 7. So again, not 1. 5 cubed is 125. We divide this by 7, our remainder is 6. So it's congruent to 6 mod 7. What about 4? 5 to the 4 is 625, which again divided by 7 leaves us with a remainder of 2 mod 7. Still not 1. 5 to the 5 is going to get us 3,125. When we divide that by 7, our remainder is 3 mod 7. Almost there. 5 to the 6. This is our P minus 1 case. This leaves us with 15,625. Again, divide up by 7, we're left with a remainder of 1 mod 7. So this is definitely not a proof, but again, just showing you for this case, we do get it raised, or when we raise it to the power P minus 1, which in this case is 6, it is congruent to 1 mod 7. All right, one more property to go here, which is basically our algorithm, or how our algorithm actually works. So we're going to go ahead and we're going to prove this one, and then we're going to formalize it more in the sense of the algorithm in itself. So here we have P, Q, N, K, E, D. Now P and Q are distinct positive primes, and we have the following. N is the product of P and Q. K is the product of P minus 1, Q minus 1. I now have to find a D, which when I compare it to K and ask for the GCD has to be equal to 1. And if the GCD of the two is equal to 1, then I know from, again, the last set of lessons here, that there exists an E such that the product D and E is congruent to 1 mod K. So if I have all of these, then I have the following. If I take B and I raise it to the power E times D, what I get back is B mod N. And this is true for every B inside of Z. So think of it this way. If B represents my message, I can encrypt my message by taking B and raising it to the power of E. Now I want to get that message back, and of course I should say this is still mod N, but if I want to get that message back, what the original encryption was, or before it was encrypted, I then take that encryption, that B to the E, and again raise that to the power D, and then I get the original message back, again, mod N. So this is the algorithm in itself. This is how it all in fact works. So let's prove this one. since it's the basis for everything here. All right, so proof. So we have a P and Q. These are our givens, distinct primes. We have K, which is equal to P minus 1, Q minus 1. Now notice what K is going to be. I have a prime, I subtract 1, another prime, subtract 1. I now have two even integers. I multiply them together. I get something that is even, so it's definitely not a prime. So the product of the two give me K. K is not prime. Now this is important because remember when we said for an element inside Z mod something, in this case we're going to say Z mod K, in order for, and when K is not prime, in order for an element, a non-zero element, to have a multiplicative inverse, so when I multiply the two, I get something that is congruent to 1, then what needs to be true is that I have to be able to take an element that when I take the GCD of that element and K, it gives me 1. So that's the condition that we need to be true down here, that we have to pick a D such that when we ask the GCD of it with K, this is going to get us a 1. And then last but not least, when this is true, we're able to find an E such that this is congruent to 1 mod K. All right, so by assumption, so basically here I'm just writing down everything that we are in fact given. Now we're going to go through the proof in itself. So by assumption, we have D, E, so that product is congruent to 1 mod K. Which of course this means that K divides the difference, so the DE minus 1, which means I could write DE minus 1 as a product of K times some T, where T is an integer. So if I take this here, I'm going to rearrange this and isolate for the DE. So DE, moving the 1 to the other side, gives me a KT plus 1. And now we saw in the last class that the actions of this is commutative, so instead of DE, I could rewrite this as ED. Again, is equal to KT plus 1. Now for any given B in Z, what we're going to do is we're going to take B and raise it to the power ED. So this is B. Now remember, ED, I've rewritten this as KT plus 1. So we're going to do that substitution in. So instead of ED, I'm doing KT plus 1. Laws of exponents, I could rewrite this as B to the power KT times B to the power 1, or we'll just leave it as B. Now K, we know what K is. K is P minus 1 times Q minus 1. So let's do that substitution in. So instead of K, I'm going to write P minus 1, Q minus 1, T times B. And we're just going to isolate B, P minus 1, Q minus 1, T, B. All right, now we need just a little bit more space here. So if P does not divide B, then from Fermat's little theorem, this tells me that B, if I raise that to the power P minus 1, this is congruent to 1 mod P. So I could rewrite this whole thing this b to the ed is equal to b p minus 1 q minus 1 t times b, which again congruent to 1 q minus 1 t b, which 1, we raise it to whatever power we want, it's still going to be 1, so this is just b mod p. Now, this is not exactly what we want just yet, because remember, what we want is b to the power ed is equal to b mod n. Right now, we're just doing it mod p. Perfectly fine. So we've made the assumption that if p does not divide b, well, what happens if it does divide b? So if p does divide b, well, then what do we know? Then b and every one of its powers are congruent to 0. Because remember, if it divides and there is no remainder, that remainder is 0, which just so happens to mean that the two things are congruent to each other. So it's congruent to 0. So again, we get that b is congruent to 0 mod p. Which I could also write this by laws of this, that 0 is congruent to b mod p. And again, I can raise this to whatever power I want. It's still going to be congruent to 0 to whatever power we want. Mod p. And again, this is just equal to 0. And since I have b to some power is equal to 0, 0 is congruent to b mod p, then we have b to whatever power, which in this case we'll say is b to the ed is congruent to b mod p. All right, so we get what we want back, again, when it's in terms of mod p. Now, we could make the same argument, and I'm not going to prove it because it's exactly the same argument. We can do exactly the same thing with q, because remember, p and q are relatively prime. So I'll just make a note here. A similar argument shows that b to the power ed is congruent to b mod q. All right, so if we have b to the ed is congruent to b mod p, and we have b to the ed is congruent to b mod q, and p and q are in fact distinct primes, then clearly b to the ed is congruent to b mod p times q, and p times q, this is our n. So there we go. This is how our algorithm works. This is the proof that it does in fact work. So the next part of this video lesson is we are going to go through the steps on how we do all of this and go through an example. We'll see you back then.